Tableau 7. Is the outcome of the toss of a coin really random? Thus far in our development of an abstract theory of probability, we have appealed to intuition from commonplace chance experiments to put together a foundation consisting of three elements. First, an abstract sample space of idealized outcomes of a thought experiment, a Gedanken experiment. These are the sample points of the experiment. Second, an algebra of events. And third, a probability measure, a set function which ascribes to events numbers in accordance with three fundamental axioms: the axiom of positivity, the axiom of normalization, and most importantly, the axiom of additivity. So far, so good. We've now got the beginnings of an abstract, fully mathematical theory of chance. But how does such an abstract theory gel with our common experience? How does it fit with commonplace chance experiments? Inevitably, we go back to the simplest settings to get a right understanding of how theory meshes with practice. And the simplest of all, of course, is the toss of a coin. And so, inevitably, we return to the toss of a coin. Let us consider what is involved in the toss of a coin. We hold a coin up with some orientation, we toss it, it lands, and perhaps it bounces. At this stage, one discerns that the process is purely mechanical. This is a physical experiment governed by physical laws. What are the kinds of laws which govern where the coin actually ends up and what its final orientation is? Well, one can think about it and say, well, the mass distribution surely should have some effect on the coin. So how is material distributed on and around the coin? The resistance of the air might play a part. The gravitational force, which could depend upon the altitude at which this experiment is conducted. Is it conducted at high altitude? Is it conducted at sea level? The elasticity of the floor, which governs the number of bounces, if the coin is allowed to bounce. And of course, the initial velocity with which the coin leaves the fingers, and the spin or the angular velocity imparted to it. So these, one could discern, are primary factors affecting how the coin moves, how it evolves, and how it ends up. But the moral of the story is that a coin toss is properly viewed as a fully deterministic, evolving, dynamical physical system. And if it's a purely deterministic physical system, it is governed by physical laws. And in consequence, the outcome should be predictable. Well, before we launch into an analysis of this, it is always wise to simplify the problem to essentials. If one looks at the situation as a whole, there are several factors which could conceivably affect the experiment, but not all of them are of primary importance. For example, the listener might well agree that the distribution of a normal coin is reasonably uniform. Yes, there is a head embossed on one side, and there's a tail on the other, but these are minor variations in the thickness of the coin, and at least to a first approximation, it might be not unreasonable to imagine the coin has got a uniform mass density. Likewise, the air resistance, one might posit that over a relatively short distance of transit, the air resistance is not significant, not primary. Similarly, the gravitational force, well, we could just posit we do the experiment at ground level. But wherever it is, we can assume, again to first approximation, that the gravitational force, the gravitational acceleration, does not vary significantly over the duration of the coin toss, over the height of the actual coin toss. Floor elasticity creates a variation on this theme. And we can eliminate it again from consideration for first principles by simply saying we just catch the coin. And at this point, we don't have to worry about repeated bounces. Now, if this is the case, then many of these factors become secondary. But of course, it is very hard to get away from the conclusion that two factors are primary and will affect the outcome. The first, the initial velocity. How fast is the coin moving? What speed is imparted to it by the flick of your fingers? And the second, the angular velocity. How fast is it turning when it leaves your fingers? So it appears that there are two fundamental physical parameters which affect the outcome of a coin toss, at least to a first analysis. So now let us consider how these two elements come into play and how they interact. So let's go back now to a sanitized model of a coin toss. Here now we have a coin and we are going to toss it, and we will simplify the experiment by assuming that we toss it and we catch it. It'll simplify the analysis if we assume that we catch the coin at the same height that we tossed it at. This is not essential for the analysis, but it'll make the algebra a little more transparent. Nothing is wise that unnecessarily complicates existence, and therefore, without further ado, here is a sanitized model of a coin toss. We begin by imagining that the real coin is modeled by a thin, uniform disk, one side labeled heads, the other labeled tails, as depicted in your figure. Now, at time 0 for the experiment, we imagine the coin is placed flat at a certain height above the ground, and we will call that the origin of a coordinate system, height 0. Now, this is a matter of definition. So let's say that this is now at height 0 at time 0. T, inevitably, will denote time. And now there are two parameters of interest to us. One is, how high is the coin at a certain time from my starting position, and how much has it rotated from my initial position. Now, there's one more parameter which can add an element of chance to this, and let's dispose of that, and that is the initial orientation of the coin. Let us say that we start with heads facing upwards. So now we've got an experiment. A coin at height 0, at time 0, with heads pointing upwards, is tossed. It is caught at the same height. A certain speed, a velocity v, is imparted to the coin, and we assume the coin is now traveling straight upwards. Inevitably, we call the height the letter y, because long experience with the calculus has inured us to calling the vertical axis y. So let's call the height y, and for similar reasons, the angle that the coin makes with the horizontal. So the moment we impart a flip to the coin is revolving around a horizontal axis. The angle it makes with that axis we shall call, inevitably, theta. So y represents height, theta the angle the coin makes with the horizontal. Of course, both of these are functions of time. At time 0, in the initial position with heads pointing upwards, the height y at time 0 is 0. The angle at time 0 is 0. So we say y of 0 is 0, and theta of 0 is 0. Now the coin is tossed. Let us consider what happens at time t. The coin is at a certain height, let's say y at time t, and with a certain angular orientation, theta at time t. As the coin progresses and comes back down, we catch it at the same height that we had caught the coin earlier. Its termination time, when we catch the coin, let's say is at time t equal to tau. And at time tau, the coin is returned to its original position, Its height is now 0 again. And when its height is 0, its angle, however, is not quite 0, not necessarily. So at time tau, it forms some angle, theta of tau, with respect to the horizontal. The hand, of course, absorbs the force of the returning coin, and the coin is then kept flat with the upward pointing face at the moment it returns to its starting point, the ultimate outcome of the toss of the coin. So at this point, we've got a coin which is returned. Its angle at time tau, at the termination of the experiment, is theta of tau, and the angle determines everything about what the outcome is going to be.